Chapter 6, Normal Distribution. Working our way up towards this idea of inferential statistics, we're going to spend some time working with some different distributions. One of the most important ones is the normal distribution, so that's what we're going to start with. This section, section 1, introducing normally distributed variables, is mostly vocabulary again, getting the idea of some of the things we're going to work with. We'll get into a lot of the calculations and working with things in section 2. So, again, the normal distribution is one of the really important distributions in statistics. A lot of the times, ideally we're going to be dealing with normally distributed variables, which we got to figure out what do we need. Well, we're doing right here, introducing the idea. What is a normally distributed variable? First, we're going to talk a little bit about something called the density curve. That's going to help us with this. And then we're finally going to convert to a standard normal distribution. Because we're not good enough just being normally distributed. We want standard normal. Boy, that sounds like redundant, doesn't it? Okay, so density curve. We kind of looked at this when we were looking at shapes of distributions back in section 2, or chapter 2, I believe. We're talking about, is something symmetrical or is it skewed? We kind of drew this smooth curve to represent what the histogram looks like. The density curve, it is a smooth curve, so it's representing a continuous variable, but we can use it also to approximate a discrete variable, which is kind of nice. To be a density curve, we need to follow these two properties. It is always above the horizontal axis you see here, and the total area underneath this curve must equal 1. That 1 is kind of a magic number when we're dealing with probability and statistics. When we're talking about relative frequencies, they all add up to 1, a relative distribution. It kind of has that tie in there. And here it is. The percentage of all possible observations that lie within a specific range is equal to or approximately equal to the area under the density curve. So, for example, over here, we're looking at where less than or equal to A. This shaded area, the area of this shaded part of the curve, is going to equal the probability. If we're greater than or equal to, we're looking to the right side of that value A, and again, the area. Or we'll look at in between two values. These are basically the three intervals we're going to be most interested in. We're either less than or equal to a value, greater than or equal to a value, or between two values. So let's look at a simple example of doing this. So here, crystals of a certain mineral are cubes. That's nice. Length of the sides is a variable, has a density curve shown below. The density curve is the equation y equals x over 2 as long as x is between 0 and 2. So take a few minutes, pause this video, see if you can figure this out on your own. What's the probability you're less than 0.5 millimeters? What's the probability you're between 1 and 1.5 millimeters? And what's the probability you are at least 0.25 millimeters? Pause the video, try it on your own, then come back and we'll work through this for you. Going to take advantage of this is a nice line, so these areas are, this is a nice triangle, so we need to just remember our formula for a triangle. Area is 1/2 base times height. We can get the area under the curve. So if we want the probability we're less than 0.5, we're going to put in the base is 1/2, 0.5. The height is, this equation was again x over 2, so that's why we get the 0.5 over 2. And we get 0.0625, or 6.25% have lengths less than 0.5 millimeters. If we want B is between 1 and 1.5, you can, if you remember your trapezoid formula, you can use the trapezoid formula. You could say, oh, look, I have a rectangle here and I have a triangle here, so we could do those in two parts and find the area of this. Actually, this is a square, and the area of this triangle we actually have right over here, because it should be the same triangle. Or, the way I did it here is I took the big triangle and I subtracted the little triangle. All three ways would give you the same answer. Doing it this way, less than 1.5 is 0.5625. Less than 0.1, or less than 1 is your 0.25. So we take the difference and we get 0.3125. The reason I did it this way, geometrically, it probably might have been even easier to do it. Probably the easiest way would have been to do it with a square and this triangle. But this is the method that we're going to be using when we look at our normal distribution and our other distributions. So I'll get that idea of, hey, I can use this idea, use this one formula, or use this one table to do everything. So last one is we are at least 0.25. We want this whole thing. Well, I know the total area is 1, so I'm just going to do the complement. So again, I can say, well, this is 0.25 right there. I'll find the area of the small triangle and take the complement. So I get 98.44% have lengths of 0.25 millimeters. That's kind of the basic idea, basic techniques we're going to be using when we work with these normal distributions. Except this was nice and easy because we have a nice formula and we can use our what we know from geometry to do this one. So as I say, not too bad when the density curve is a line. But if the curve is getting more complicated, we don't have fancy or handy formulas to use. We need calculus. The integral calculus is basically a way to take an equation of a curve and find the area between the curve and the positive horizontal axis. Yeah, we're not going to do calculus here. That's why we want some known distributions. So the idea is if we can fit our data and make it fit a distribution I already know the numbers for, then I don't need the calculus. Someone else did that work for me. So this is where we're going to get to this idea of the normal curve. Last chapter we were dealing with the binomial distribution. Discrete data from a series of Bernoulli trials that made a nice symmetrical distribution, which looks kind of like this. And this, basically, we get a symmetrical curve, looks like an upside down bell. This is why it's often called the bell curve. But it's very usual to find this shape with data when we're doing this work. So we call this the normal curve. So if you hear about a bell curve or a normal curve, we're talking about the same thing. We're talking about a nice symmetrical distribution. So this is another one of these wonderful definitions. If a variable of a population is normally distributed and is the only variable under consideration, common practice is to say that the population is normally distributed, or that it's a normally distributed population. So what do I mean if the variable is normally distributed? That means if the distribution has that bell curve shape, that shape of the normal curve. So if the variable is normal, we say the population is also normally distributed. But, as I say, we see this a whole lot, but we actually never really see it because nothing's perfect. And we very seldom have an exact normal curve. But a lot of the times we have something that's close enough that looks roughly normal. So sometimes we'll just say, oh, this is approximately normally distributed. But we will still treat it as if it was normally distributed. But keep in mind, real life has errors, right? So when we talk about the normal curve is defined by two parameters, the mean and the standard deviation. Any normal curve, all we need to know is, I don't need to know anything else except what's the mean, what's the standard deviation, and I can represent the normal curve. We'll do some work with decimals in the future, where on decimals you can draw a normal curve. All you need to do is tell it, hey, what's my mean, what's my standard deviation? It'll graph your curve. That's actually how I made this graph here. So any two curves, if you have the same parameters, they're going to be identical. So if we look at these, all three of these curves, you notice they are symmetrical with respect to the mean. Let's get that disappeared. So on this one, this peak is at 10. Here mu is 5. When that disappears, you'll see the peak is going to be at... No, it's not going to disappear for me. Okay, do it. Go, go, go. There we go. At 5. The orange one, you notice the peak is at 16. Mu equals 16. So that peak, that line of symmetry is at the mean. The standard deviation says how spread out apart it is and how tall it is. So if you notice, as sigma gets bigger, it's spread out farther, and the peak is lower. Because again, the whole total area always has to equal 1. So if we spread it out wider, the peak has to come down lower. As sigma gets smaller, it gets tighter together, and the peak gets higher. But again, we talked about this again with when we talked about standard deviations. Normal distribution follows the 3 standard deviation rule. Almost all of your observations are within 3 standard deviations of the mean, as you can kind of see in this graph here. You know, there's a little bit once you get past mu plus 3 sigma or mu minus 3 sigma, but it's basically really hard to see that. So let's put this into effect or into practice. Here's a table. This is looking at enrollments of 3,264 female students, showing the mean height. Or sorry, not showing that. You can, if you calculate from this data, you'll get the mean height is 64.4 inches and the standard deviation is 2.4 inches. So here is our frequency distribution and a relative frequency distribution. So what we're going to do is look at this and see that it is normally distributed. We're going to identify a curve that fits this, and then we're going to look at what that really means. So, to start off, if we graph this, we graph that relative frequency histogram, you will notice this is not perfectly symmetrical. You can see right here, but it is as practically symmetrical as you can get. You know, it's practically there. So this is fairly symmetrical. It is normally distributed for the population. If we take that mu equals 64.4 and sigma equals 2.4 and we graph that normal curve over top of this histogram, you notice that this matches up pretty well. We come up here, the 64.4, here's 64, it's right up here on my highest there. And we got a little above, a little below, because this is discrete data, it's not continuous. We have those jumps, but it's a pretty fair representation. If you were going to draw, you know, a smooth curve over this, you'd get something pretty close to this. So we can say it's normally distributed, and we can represent it with this normal curve. And we can see that when we look at, we're going to just look at one category. So if we look at the heights between 67 and 68, if you look on the table, the relative frequency was 0.0735. If we look at the area under the curve for that interval, you actually get 0.07, which is pretty darn close. So we could use, Instead of having to have this whole table and all of that data to represent and to do some figuring with probabilities and working with that, we can just say it's normally distributed. Mu is 64.4, sigma is 2.4. We can use technology to make this graph. We can use tables to look up the values we need. We no longer need to have that data. And that's the advantage of using a being able to fit it to a known distribution. So the problem is, now that we have with computers and we can say, here's my mu, here's my sigma, and have it do your distribution, and you can do the calculations with that. But, you need a different set of values for every different mean and every different standard deviation. Or you need calculus to be able to attach that. So, the idea is if we can standardize this so that we can take every single problem and turn it into the exact same distribution, then I can look it up on a table. I only need one answer that I can use to do all of it. And that's this idea of the standard normal distribution. Standard normal distribution is this one right here. The mean value is 0 and the standard deviation is 1. And if we have a normal distribution with a mean of 0, standard deviation of 1, this is a standard normal distribution, or the standard normal curve. And that should sound familiar, because that idea of mu equals 0, sigma equals 1, that's how we got our z-scores to standardize our scores. When we talked about, again, when we're doing means and standard deviations, we said here's our standardized score, our z-score, so we can compare different data sets. This now is going to help us, because if we change it to z-scores, we can make any normal distribution fit the standard normal distribution. So you're going to need that formula z equals x minus mu over sigma. In this section, we're not actually going to do any work with this. We're, again, doing a lot of introducing the vocabulary. Next section, we will start doing our calculations, and then the fun really begins. So let's see what you think about all this definitions. Let's work on this assignment, and I'll see you next time.